Hello everyone. So in this video, we are discussing one of the past years of basic econometrics. This was being conducted in 2023. So you need to attempt question 1 and any other 5 questions. But we'll be discussing all the questions in this video. Now, you can read the first question. Provide reasons and state whether the following statements are true or false. In the regression model, log y equals to beta 1 plus beta 2 xi plus ui. If beta 2 is multiplied by 100, we obtain the growth rate estimate of yi. So we know this statement is true, and writing the function as beta 1 plus beta 2 xi plus ui. Now differentiating this 1 by y dy equals to beta 2 dx. So this becomes del y by y upon del x equals to beta 2. Now if you multiply this by 100, so this gives us the growth rate. This thing would give us the growth rate. So this is the relative change in y for a absolute change in x. So beta 2 into 100 would give us the growth rate estimate of y. So this is true. Now coming to the second part, adjusted r square is always lesser than unadjusted r square. So we have discussed that r square is a goodness of it. So it shows the range of r square lies between 0 and 1. It shows the proportion of variation in dependent variable which is being explained by the independent variables. And even if we keep on adding variables, r square is bound to increase. It will remain same only in the case when the variables are totally irrelevant. And adjusted r square only increases when the t value, the mod t value of the variable that we are adding to the model is greater than 1. So adjusted r square increases only when a relevant variable is added to the model, whereas r square may, or in most of the cases, r square increases and it would remain same when the variables are irrelevant. Okay, now so this is also true. Now looking at the third statement, ceteris paribus, like keeping other factors constant, the more dispersed are the sample regressive values in a linear regression, the greater is the variance of its coefficient. So we know this statement is also true. Now looking at the fourth statement, if p value of a test statistic is greater than the chosen level of significance alpha, then we reject the null hypothesis at the alpha level of significance. We know when p value is less than alpha, we reject the null. But in this case, it is being mentioned that p value is greater, then we will reject the null. So this statement is false. Okay. Now coming to the fifth statement, you can read the question. Regression model yt equals to b1 plus b2 plus b2 xt plus ut. If the OLS residuals are plotted against time and a distinct pattern is observed, then it indicates the presence of heteroscedasticity. But look at one. So look at this thing. Heteroscedasticity is concerned with cross-sectional data, not with time series data. So this thing is of autocorrelation, which is a time series phenomena. Okay. Now coming to question 2. You can just have a look at this question. Now in this case, we are supposed to find a from 5-year data. So n is 5 here, of profits earned in thousands of rupees. Y denotes profit and amount of goods produced in million units, and x denotes amount produced. So your profit would be dependent on a plus bx. So we will have a linear function of this form because they have asked us to find the equation of the linear regression line of y on x. So profit is a function of the amounts amount produced. Okay. Now with the help of the normal equations, you know summation yi equals to na plus beta summation xi, and summation yi xi equals to a times summation xi plus b times summation xi square. Since we have two equations and we need to find two variables, we can solve this. So we'll get the value of a and b, and accordingly we can find the line, regression line, right? Or else we can find the value of beta 2 hat. This is b, or suppose, okay, b, or which we usually denote as beta 2 hat. This can be written as summation xi yi upon summation xi square, where xi is xi minus x bar. Similarly, yi is yi minus y bar, and xi yi is product of summation xi yi is yi minus y bar. I hope this is clear. Now, okay, so we are done with the first two parts. Okay, in the second part, we are supposed to find the residual sum of squares. The residual sum of square is, so we have total sum of squares, which is equals to explained sum of squares plus residual sum of squares. Explained sum of squares in this case would be beta 2 hat square summation xi square. Total sum of squares is summation yi square. So residual sum of squares, you can find it as total sum of squares minus explained sum of squares. So you will get the residual sum of squares. Now the third part, they are asking what proportion of the variation in y is explained by x. They are asking nothing but r square, and r square is defined as explained sum of squares by total sum of squares. So you can find the value of r square as well. Now looking at the fourth part, they want us to test at the 5% level of significance whether the slope coefficient is greater than 2 or not. So our null hypothesis would be beta 2 equals to 2, h naught is, and h1 would be beta 2 greater than 2. With the help of beta 2 that we have already found through this or through the normal equations, we can check and we can verify whether it is coming out to be greater than 2 or not. And accordingly, we can find whether the slope coefficient is greater than 2 or not. So, and talking about this fifth part, this part has been removed from your course. So you are not supposed to study this for the exam purpose. Okay. Now moving to question 3, first part. So we have a regression model of data from 34 retail stores, where y is the monthly sales of a good which is dependent on price. So it is expected it would be negatively related to price. And x3 is the in-store promotional expenditure. So higher the expenditure, it is expected higher would be your sales. Now you are supposed to, in the first part, you are supposed to interpret the estimated partial slope coefficient of x3. The coefficient of x3 is positive 3.613. So this means, and this is in thousands. So if you increase the in-store promotional expenditure by 1,000 rupees, it is expected that monthly sales would increase by 3.613 units. Okay, I hope this is clear. In the second part, you are supposed to calculate the value of r square. So since we have already discussed, r square is nothing but explained sum of squares upon total sum of squares. And in this question, the total sum of squares is given to you. Residual sum of squares is also given to you. We know this as well. So since we know the residual sum of squares as well, we can accordingly find the estimated, the explained sum of squares as well. So accordingly, we can find the value of r square, and adjusted r square, the formula is n minus 1 upon n minus k. I'll just and adjusted r bar square is always less than equal to r square. Okay, and if we are talking about the overall goodness of the fit, we need to use the F test. Similarly, you will find the value of this and you can check it at the alpha equals to 0.01. Now, talking about the steps that you are, okay, talking about this B part, the steps required to test for the normality of the population disturbance term. We have various tests. Normal probability plot is there, but one of the normal probability plot, one of the main test is Jarke-Bera test. I'll write it here. Jarke-Bera test. So the Jarke-Bera statistic value is s square by 4 plus k minus 3 whole square by 24. This is 4 or 6. So skewness should be 0. Kurtosis should be 3. And if, so this follows the chi-square. And if the value is closer to 0, so our null hypothesis in this case is that the disturbance term follows normal distribution. And H1 doesn't follow a normal. So if the statistic value is coming out to be very high, it would mean that the disturbance term doesn't follow the normal distribution. Okay, now coming to question 4. So they have introduced a dummy variable in this case. You can look at the question. They are giving you the relationship between income and savings. So we know savings would be positively dependent on, income, which means if income is high, it is expected that savings would be higher. So they have 2 time periods and they have used this interaction term as well. So dummy d equals to 1 for period 1, 0 for period 2. What is the base control category for this regression? So we know we need to put d equals to 0. We'll have yt hat equals to d is equals to 0 is for period 2. So period 2 is the base category. So we have, okay, we just need to tell which is the base control category. So period 2 is the base category, which is from year 1974 to 88-89. Is such a model called, and it should not be there, ANOVA model or an ANCOVA model? This is an ANCOVA model because they have included the interaction of these terms as well. They have included the dummy variable and interaction of these terms as well. Interpret the meaning of the coefficient value 0.075. Okay, so we are supposed to interpret the meaning of this intercept. So initially, the slope of the curve is 0.249, which means yt equals to something plus 0.249 xt. So if you're talking about the base category, so this means if income increases by 1 unit, X is income. If income increases by 1 unit, savings would increase by 0.249 unit. And we have this another term, dtxt, which means dt would take a value 1 in case of period 1, which is from 1989 to 1995-96. So this would mean in period 1, the savings would have actually increased by xt plus 0.075 xt. So savings would have actually increased by, I don't want to find the value, you can find it by yourself as well. So if there is a 1 unit increase in income, in period 1, the savings would increase by this much unit. So it tells you the extra amount of savings which are being done for 1 additional increase in income in period 1. Okay, now you need to test whether the model suggests the presence of structural change in the two periods. Structural change can be incorporated, can be observed when these variables are significant. Because if this variable is significant, which is having a t-value of minus 2.945, which is significant, so this states that there is a significant difference in the intercept in both the periods. And since this slope coefficient, the extra incremental slope, is also significant and positive, this would mean in period 1, the savings rate, or the MPS, marginal propensity to save, is higher. So there is presence of structural change in the model. We are supposed to write out the regression equation for period 2. So in period 2, what we have is, I'll write it here. For period 2, yt is taking, yt hat is 959. This will take value 0. This will take value 0 since we are talking about period 2. Plus it would be 0.249 xt. This would be the equation for period 2. Okay. Now coming to question 5. In order to check for the presence of multicollinearity in the model, an auxiliary regression was conducted and the result is this. So auxiliary regression means you are regressing one of the independent variable on the other independent variable. Since R square is coming out to be very high, this means these variables are highly correlated. Variance inflation factor is nothing 1 minus R23 square, that is the correlation between 2 and 3, variable x2 and x3. So in this case, this would come out to be 1 minus 0.910. So a value greater than 10 indicates that multicollinearity is present. And we know when multicollinearity is present, the betas are unbiased. They are not blue, but they are unbiased. They are not efficient. We have studied this, that they have larger variance, right? Now, without conducting the auxiliary regression, how could one detect the presence of multicollinearity? There are different methods. First is high R square, then VIF, then insignificant T ratios, and then we have tolerance factor. So 4 or 5 of them are enough. Now you are supposed to write 2 remedies to deal with their problem of multicollinearity. First is, you can do nothing because it doesn't impact your estimates. It actually makes your estimates more precise. Second, what you can do is you can add new data to the model. Because if you add new data to the model, it is a sample phenomena. Multicollinearity is a sample phenomena, and if you will increase the sample size, the problem will automatically disappear. If you know if you have some idea about the relation between the explanatory variables, you can transform the variables as well. Okay. Now the limitation is, if you are able to transform the data, you should have done it. You need to know the exact linear relationship between them, and adding new data is also not feasible, because if you already had the data, you would have already used it. Okay. Now coming to question 6. So in this model, the average wages W, regression of average wage on the number of employees for a random sample of 30 firms. So we have this regression equation first. We have the second regression. How would you interpret the two regression? On an average, if the number of employees worker increased by 1 unit, the average wage would increase by 0.009 units. And for the second model, if the number of worker increases by 1 unit, So the average wage would keep on falling by this rate, because for the second worker it would be this, for the third worker it would be this. So the average wage that the employee would get would keep on falling in this case. Now, what might be the reason for transforming regression 1 into regression 2? Okay, what assumption has been made about the error variance in going from regression 1 to regression 2? So we have studied in case of heteroscedasticity, if we have a error term of like this form, so we'll transform the model by dividing it by n1 throughout. So we can see in this case as well, we have divided it by n1 only. So it might be the case that it will be the case that the errors term is dependent on ni square, that is number of workers. Can you relate the slope and intercepts of the two model? If you will multiply this by ni, the whole equation, you will get somewhat similar to this equation only, which is coming out to be 7.8 plus 0.008 ni, which is more or less similar to this only. Now, can you compare the R square of the two models? Since the dependent variable has a different form in both these cases, so the R square cannot be compared. To compare R square, we need two things. First, the dependent variable should be of the same functional form. Second, the sample size should be same. Okay. How would you check for heteroscedasticity? Test its existence and then remedy it. We have white test with us. We have Goldfield quant test. We have and then we have Spearman rank correlation test. We can use either one of them to test for it. And some of the remedial measures are, so if we know the error term, like if we know how the error term is correlated with the explanatory variables, we can accordingly transform the data. So if it is sigma square by ni, we'll transform the model by dividing it by root ni. If it is ni square, we'll divide it by ni. So we can do this if we already know how the error term is related. Okay, so this is the last question. So this is a logarithmic regression of demand for food on price and personal disposable income. So it is expected as, since it is a log model, this would show the elasticity. 1% change in one of the variables impacts what percentage, how much. So in this case, if price increased by 1%, quantity demand would fall by 0.31%. This is how we are supposed to interpret it. Interpret the value of the coefficient 0.31. Sorry. So this is a negative sign which states if price increases by 1%, quantity demanded would fall by 0.31%. Similarly, just by now, we are supposed to do the second part. Just by looking at the estimated regression, do you suspect serial correlation in it? Now this is price, this is income. So the quantity is itself dependent on the previous year's quantity. So this would be a time series data, and it is expected that since this term is being included, serial correlation is bound to be there, because the quantity you purchase in this year of food would more or less be similar, or there would be few difference between what you consume this year and in the next year on food. Now, which test do you use to confirm your suspicion and why? So if we are talking about autocorrelation, we use Durbin-Watson test, because they have given you the value of D as well, which makes your work more easier. So we are supposed to use Durbin-Watson test. Now in the fourth part, you are supposed to outline the steps of the above mentioned test and provide a conclusion based on your calculation. So for all those who have studied Durbin-Watson test, its range is from 0 to 4. Here we have dl, then du, 4 minus du, 4 minus dl. So the Durbin-Watson value is 2 times 1 minus rho. Rho is the, okay, rho is how the error term is distributed. So the correlation between the error term and the error term of the previous, the coefficient denoting the error term of the previous period. Now if rho is exactly equal to 1, that is there is positively plus 1, that they are positively correlated. So d would take value close to 0. So this portion suggests positive autocorrelation, and this portion would suggest negative correlation, because if rho is minus 1, d equals to 2 times 1 plus 1, which is 4. This shows positive correlation. This is a zone of no conclusion. This is a zone of no conclusion, and this zone, in this particular zone, we do not reject the null, that there is no presence of autocorrelation. So if we lie somewhere here, there is no autocorrelation present in the model. Now the fifth part, you are supposed to state the conditions under which you may choose different tests for serial autocorrelation. What are the different tests? One we have is runs test. So basically in this part, you are supposed to tell some of the shortcomings of Durbin-Watson test. So one of the shortcomings of Durbin-Watson test is it assumes that the error term are supposed to be normally distributed. Okay, and the second issue is they assume that the error terms follow. So the error terms is dependent on the past year error term, but this cannot be the case. That is, it should be restricted to one past year term only. Okay. And then there is an important assumption that intercept should be present in the model. Should be there, or else you cannot use the Durbin-Watson test. Fourth, the lagged value of the dependent variable should not be there, as one of the dependent variable should not be there as one of the regressors, as one of the independent variable. So we can see, I'm marking it with green, log qt minus 1. So in this case, we cannot use the Durbin-Watson test. Okay, I hope this was clear.